In this clip, I wish to go over the solution to quiz number 6. In this first question, we ask you to prove the theorem. So if you have the flashcard with you, just lay that theorem side by side with your work, and you just check one condition of another in that order before the theorem is applied. So we start with sine of 1 over x between -1 to +1, okay, greater than or equals -1 and less than or equal to 1. Here we mention x not equal to 0, mainly to guarantee that sine of 1 over x is defined, okay? And then because x squared is greater than 0, right? Under the circumstances, which is x not equal to 0 in the domain of the function, so we multiply x squared on every side. And we organize the term. Right? We just organize the term. And the limit of the two functions from the bottom and from the top are equal to 0. Therefore, by Squeeze theorem, the functions that squeeze in between has a limit 0, and that is done. So by this time, that is the end of proof. There's a common mistake I identified is that some people, when on this step, they just multiply x squared like this. Whether you have this dot or not, it will be viewed as x squared minus 1. Therefore, this missing a parentheses here is a mistake. Okay, you should just be careful not making this kind of mistake. The second question. Okay, so here's my answer. There are different versions of the answer. Okay, so my version of the answer, I started with, right, because asking, is it continuous at 1? Is it continuous at 2? So I go by that order. But I first indicate the domain of this rational function is x not equals to 1. And then I say the rational function is continuous everywhere in its domain. Okay, so this statement, I'm quoting a theorem we learned that a rational function is continuous everywhere. So this statement is going to be very powerful for me to say what I need to say next, right? So I go ahead to say, f is not defined at 1. Well, 1 is not in the domain, therefore it is not continuous at 1. So here I answer the question whether it's continuous at 1 or not, right? And quoting one of the definition of continuity, where the function is not defined at the point of consideration. Number 2, I said, is 2 continuous? Is function continuous at 2? The answer is yes, because all I have to say is 2 is in the domain, because 2 is not 1. The only number that's not in the domain is 1. Now, 2 is in the domain. According to this theorem, f of x is continuous at 2. And thirdly, we're working on the removal of the discontinuity. So I take limit when x approaching 1, because 1 is the point where the function is not continuous. So we continue, we'll work these steps out, okay? Some people have done the factoring wrong, okay? You may like to review your factoring technique. And we have review lessons in week 1. The discontinuity is movable if we redefine the function. So the function that was given before, that's true for x not equals to 1. For x equals to 1, we're going to define it to be the limit of the function when x approaching the number 1, which is the point of discontinuity. So this way, we made 1, 2, 3, the 3 conditions of continuous function to be true. Okay, no. I found this mistake in a lot of you guys' work, okay? Several. First of all, if you say since if f is not defined at 1, it is continuous. It is not continuous, no problem. This is a true statement. However, if you say since f is defined at 2, therefore it is continuous, that is false, okay? Especially those of you who made this statement did not mention this all-powerful theorem, right? So you only have if definition at the point, you still need to prove 2 other items to demonstrate it is continuous. Okay, so be careful. This statement is true, but this statement is false. So for those of you who made this kind of connection, okay, that's a mistake. But it happened to be true in this case, but you do need to mention it's a rational function and its domain. That will make your argument more appropriate. Okay, third one, the third one. The third one, some of you did a substitution directly. No, you can't do substitution directly. So if you like to show work, this is how you show work. As x approaching 3 from larger than 3, x squared minus 9 approaches 0 from larger than 0. So natural logarithm approaching negative infinity. Okay, so that would be sufficient. And you don't have to know the curve, but if you really want to use the curve, and ln(x) will be a good curve to use. And you don't have to know the exact curve of this ln x squared minus 9. You don't have to. But if you happen to know it, that will be helpful. But in this case, all I used is this curve. Okay, I did not use this curve, but I'm using this curve. This curve says, okay, the domain of a logarithm is, it has to be greater than 0. Okay, so in our case, this is ln x, right? So for ln x squared minus 9 for this function, right? So the domain here, x must be greater than 0. And in ln x squared minus 9, x squared minus 9 must be greater than 0. Okay, that's to determine the domain. Oops, sorry. I'll have to change it to the proper mode. Okay, domain, right? For this domain determination, you will have x squared larger than 9, and you take square root on both sides. Okay, we take square root on both sides. We take square root on both sides. That's going to be greater than 3 because square root of 9 is 3. And then you have the absolute value. Have the absolute value of x is larger than 3. So your domain is x less than negative 3 or x is larger than 3. So you actually have 2 pieces, okay? So the actual curve of ln x squared minus 9 actually is going to look like this. You have 2 pieces. You have 2 pieces, but you don't really need this curve because the given function is sufficient. The given function is already sufficient. So let me adjust the curve for you. Okay, so you can see that these 2 curves are like this. You have 2 vertical asymptotes at a negative 3 and positive 3. Okay, let me bring that up. Okay, I'm going to draw for you the vertical asymptotes, but you really don't need these information, okay? The first curve is sufficient. Okay, so that's a vertical asymptote, but I just want to, since I mentioned this, I'm just going to complete it, right? So give you the whole picture. There we go. So we have these three vertical asymptotes, right? So when x is approaching 3, right? When x is approaching 3 from larger than 3, so we don't see this piece. We don't see this piece. We only see this piece. Okay? That's what x approaching 3 from larger than 3, this way. This part is not relevant. Okay, so here, whoops. Drawing. Okay, so this piece is not relevant for our work for this particular question, and the curve x is approaching 3 from larger than 3. Okay, so that's why. Okay, that's why this piece of function is sufficient, because all we need to know is what x squared minus 9 approaches to. And then we know x squared minus 9 approaches 0 from larger than 0, which is well in the domain. Okay, and so you can see the function's value approaches negative infinity going this way. All right, so you should know the ln curve. We have reviewed that in the first week function review, right? So take a look. If you need more information, let me know. I can help you to find out those other information. But you can see we use variety of functions in our calculus study. Thank you for watching.